Hi, everyone. Thanks so much for coming. Today I'm going to talk about fully remote vulnerabilities in messaging applications. I'm Natalie Silvanovich, and I'm a member of Project Zero at Google. And fully remote mobile vulnerabilities and exploits is something that we've been interested in for a long time. The thing is, it's one of those things where there's lots of rumors and speculation, and not so much actual technical information. For example, early last year, Chowki Bakrar made this tweet where he pretty much compared the security of the different messengers from a zero-day exploit perspective. And this was especially interesting because Chowki runs a company called Zerodium that publishes this public price list for all sorts of exploits for all sorts of targets. And you'll see near the top, there is zero-click exploits in WhatsApp and iMessage, and then Signal and Telegram lower down. And to me, this indicates that these exploits probably exist and are probably valued by attackers. Around the same time last year, this article came out about the UAE secret hacking team. And it talked about a tool called Karma that accesses data on people's iPhones. And they specifically said that it did not require the target to click, and that it relied on an undisclosed vulnerability in Apple's iMessage software. So this is another piece of evidence that attackers are using this type of vulnerability. Finally, May of last year, WhatsApp actually detected attackers using a zero-day vulnerability against their iOS client in the wild. And it was a fully remote zero-click vulnerability. So I think this is the best evidence we have that attackers are actually using these vulnerabilities for all sorts of things. But while there is all this indication, there's not a lot of technical information available publicly. So what we wanted to do was close the gap between the private attacker knowledge and what's available publicly. And specifically, the questions we wanted to answer was, do these bugs exist? And if so, where, in what component, and how do they work? That's what I'm going to talk about in this talk. And then afterwards, Samuel Gross, another member of Project Zero, is going to talk about how to exploit these bugs. Because every so often, there has been a bug found that could theoretically be fully remote, even going back to things like stage fright. But there hasn't been a lot of information about whether it's possible to exploit it. So Samuel is going to talk about his exploit for iMessage, which I think is probably one of the first fully remote exploits of this type to be made public. So what makes a bug fully remote? Well, so they're also called interactionless and zero-click, and there is a few requirements we had for this research. The first one is no user interaction required, like absolutely none. Like you can have your friend, take a device out of the box and install the messenger, and then you can use the exploit right away. No proximity. There are exploits that involve, say, being on the network path or using Wi-Fi or Bluetooth locally. And these are still important, but they're not what we were looking at here. Also, short wait time, which I'm not going to quantify, but sometimes, there's bugs where they're like, oh, well, the person's eventually going to unlock their phone or eventually do this or that. And nothing we looked at relies on that. And also, we were looking for bugs that required a reasonable set of identifiers. So pretty much, however you contact the person on the messaging application, usually their phone number or email address, once bugs start to require more complex information, like, say, someone's IMEI, they become more difficult for attackers to use. And finally, some messengers have a concept of friendship or contacts, where there's additional features you can use if someone's a contact. And we looked for bugs specifically that don't require that type of feature. Once again, bugs that do are still important, but it's another step that an attacker has to complete if they want someone to, say, be their contact or their friend on a messenger. So thinking about this more theoretically, what sort of bugs could be zero-click? And there's kind of two classes. The first is memory corruption vulnerabilities. And we looked for these, although one of the challenges is these mobile messengers often don't have a lot of native code, and definitely don't have a lot of native code that is available in the remote context. And if you do find a bug, which we did, exploitation is challenging. And when we started this project, we didn't know how you would exploit a bug like this. On the flip side, there's also logic bugs, but they're rarer than memory corruption bugs. And quite often, they're not that versatile. If you have a terrible memory corruption bug, sometimes if you put in a lot of effort, you can make it execute code. But typically for a logic bug, you get what you get, and that's it. One thing that we did find, though, is that bugs that expose attack surface can be very helpful. For example, imagine you have an image parser that gets executed after the user clicks. Sometimes there can be bugs that move attack surface forward, move it so that now you don't have to click. And I think this is a very promising way to find vulnerabilities that are fully remote. To give two examples here, sorry. I looked at WhatsApp. This was, I think, one of the first messaging clients I looked at. And I looked at the Android client, and the native code was actually very limited. Pretty much the only native components in Android are image processing and video conferencing. And image processing actually has a lot of limitations in that most of the interesting image processing is done on the send side. So if you found a vulnerability, someone would have to send someone that image as opposed to receive it. So I didn't look at that attack surface much because of that. So I looked at first what's called video conferencing signaling, which is when a call is set up, you have to say things about your device and figure out the stream. And that's a fully remote attack surface because typically they'll exchange this information before they even ring for the other user. I looked at this. I found a few minor logic bugs, but nothing too exciting. And then I looked at the video stream. RTP is the protocol. And I found one bug there in video processing, but unfortunately it wasn't a fully remote bug. It was a bug that required one click. And then later after this research, that WhatsApp 0-day was detected in the wild. And what was interesting about it is it had, it used bugs that were fairly similar to what I found. But what they did is they used a logic bug to pretty much move the protocol processing for video conferencing forward so that now it was fully remote. And now this protocol that's very prone to memory corruption flaws was available to attackers without picking up the call. So I thought that was, an especially interesting way to put things together to make kind of two bugs that alone were not fully remote into one bug that was. Another example of this is I found a logic bug in Signal, and this is what I would give it as an example of quite a quality logic bug. It was pretty much, you could send a message to the Signal client, and it would pick up the phone, and then you could listen through the microphone. And this was a very interesting bug in its own right, but it's also useful for increasing attack surface. Signal already processes a lot of data before you pick up a phone call, but if you can pick up a phone call, there's now even more attack surface. So I think this bug was even more concerning, not just from the perspective of being able to listen to someone, but also from the perspective of, I think it makes a lot of other vulnerable things available to attackers. So when doing this, a general process, at least for mobile applications, is to generally start off by determining which components have native code. And some messengers, they have so much native code that that's the only step I do. They have enough that there's a lot of vulnerabilities in there. And also, you have to figure out which ones are reachable remotely. But some messengers do have a lot of this, and some have not so much. And then the ones where this is not possible, then it makes sense to start looking for ways to increase attack surface and see what can be moved forward to make it fully remote. So now I'm going to talk specifically about what we did with iMessage. And iMessage was a bit special in that I feel that it has a uniquely large remote attack surface. Compared to basically anything else I've looked at, there was just so much processing done in native code. And I think part of this is because it's written in Objective-C. Meanwhile, a lot of clients are written in Java or Swift. And it also had a lot of formatting features, including extensions, which I'll talk a bit about later. And I worked with Samuel Gross on this, and he's going to talk about the exploits for these bugs later. So we started off by writing an iMessage sending and intercepting client. If you can do this first, it really helps. Then we could look at the messages, and we were able to also send messages to test how things worked. It really sped up our ability to look at these bugs. So we did this by using Frida to hook the incoming and outgoing messages, and we did this on both Mac and iPhone. So this was a good tooling to be able to test out bugs. And from this, this is what a message looks like. And it's in the binary plist format, which on iOS is used to do all sorts of things. Some of the interesting fields is, you can see there's the text content. And then there's this BID and BP. These are related to extensions. So you know how there's this feature on the iPhone where you point the device at yourself and you talk, and then the giraffe's mouth moves at the same time as your mouth? That is an extension. So the way this works is that'll be serialized and put into this BP field, and then the BID will tell iMessage what type of data it is. So it'll say this is type giraffe, and then the other side will know how to decode it. There's also the ATI, which is also a blob of serialized data that contains information about the message. And we didn't look at this as much, but it is somewhere that's also available to deserialize stuff. And also, there's the P field, which is the participants. You can send an iMessage to a lot of people if you want. So we looked more deeply at this serialization, which is the BP and ATI fields. And the way this works generally is that every class that you can deserialize will have a function called initWithCoder defined, which defines how it gets deserialized. And this we thought was especially promising because there were several past bugs in initWithCoder functions, including some that were found by Ian Beer. So here's an example of how the serialization works. So this is a serialized object. You can see on my right, there is the class hierarchy. So there's NSURL, NSObject. And that's the type of the object you're trying to deserialize. And then it will call initWithCoder for the URL. And then that will, in this initWithCoder function, pull out the stuff it needs to initialize the URL. In this case, you can see the NSBase and NSRelative on the other side. And these are references to objects. The 0, 1 is just null, but the 6 is actually a reference to this string on the other side at the very top column. So it'll pull out this string, and then that will be the URL for the URL. It will initialize this object and return it. So where does this actually happen? So when we looked at iMessage, for the BP field, this deserialization happened in Springboard. So this was good because it was an unsandboxed process, though it's not anymore. The serialization is now done in IMD persistence, which has fewer privileges and is sandboxed. This also is done in mobile SMS with one click, so that's not that interesting. And then the IM agent process does the same thing with this ATI field, so that's another option for using bugs in deserialization. So this deserialization does have some security features, which are called NS secure coding. And there's kind of two big things this does. The first one is if an initWithCoder from a class is used, it has to extend another method in the object. It has to extend the second method. And this basically means that you can't accidentally release an initWithCoder. You have to intentionally extend this function so that you're kind of putting in a flag that says, yes, I'm doing this on purpose. But the other thing, which I think is more important, is that it requires the developer to say what they want to deserialize, either a list or a single thing. So this prevents, you want a string, but you get an object back. And that's really important. Although, unfortunately, there are what they call safe deserialization and unsafe deserialization. And there's methods for each. So NS secure coding is not necessarily enabled. And unfortunately, these have very similar names. So for example, this one is safe and this one is unsafe. And you'll notice these are very similar, and I am sure no one ever messes up which one to use. So that was concerning. So our first idea was, let's see if we can find some accidental insecure calls. And our idea was, let's see if we can do that and then initialize a WebKit instance. And then there's lots of vulns in WebKit, so it would be easier. And exploitation's well known, so it should be easy to start exploiting at that point. But we actually looked through every call, and they were all secure, even though they're a bit confusing. So that was good. So then we decided, let's see if we can find an extension that misuses a deserialized object. So pretty much, extensions can implement their own deserialization. They aren't bound by this NS-keyed archiver stuff. So we went through all of these, and we found what I'd call one kind of inferior bug. This extension called Digital Touch, which you can use to draw images in iMessage. It would deserialize some arrays, but it would trust the length. So this could end up reading way out of bounds, but that was just a read out of bounds, not really an exploitable issue, so we moved on. So the other thing we did look at here is, can we use these extensions to once again load a WebKit instance? Because there's one extension called link presentation, and that's when you send someone a link, you'll notice in iMessage, you get a preview, and we thought, well, maybe that preview involves WebKit. But it turns out this was actually very well designed. When you send a link using iMessage, the person who's sending takes all the risk. On their device, it gets loaded, and then on their device, it gets turned into a preview. So it never gets loaded on the receiving device. And we did look and see, is there a way we can trick this and get it to load a WebKit instance on the receiver? But we couldn't find any. So our next idea was, let's look at all the legitimate deserialization, all the init with coders, and see if they have any bugs in them. And this actually turned out to be quite a big attack surface, because in iMessage, there's typically these 7 classes that they deserialize, NS dictionary, NX string, etc. But then also, all their subclasses can be deserialized. And the way the subclasses get included is they're from every single library that gets loaded by iMessage, or in this case, Springboard. And that's quite a lot of libraries. So this ended up being, I think, probably about 80 to 100 objects that we reviewed the init with coders of. And we found this bug. This is actually an interesting logic bug. Pretty much, there was an NS data class that when it was deserialized, it would load a local file. And this turned out to be problematic because it kind of had 2 problems. Problem number 1 was that it trusts the length of the deserialized file. So if you said, this is a 100-byte file, but it was actually a 10-byte file, the rest of that memory would be uninitialized. But more importantly, they did have a check to make sure this was a local file, that you were not fetching something from a URL. But that check was defective. So with that ability, you could actually use this to pull a file off of a device. And the general idea is you would use this NS data, which would load the file into the buffer. And then using other deserialization, you could append this data to an NS URL. And then you could use the bug again to visit that URL. And then that URL would have appended as a URL parameter all the contents of that data, of that file. So that was pretty cool. But then we moved on. We had a thought, which is, what if a class does not have an init with coder and you try to serialize it? And it turned out that normal inheritance rules apply, which was quite interesting. So for example, when you initialize an NS data, you call init with capacity, and almost every NS data class will extend init with capacity to initialize their memory. But let's say you deserialize an NS data that extends, or you deserialize a class that extends NS data. If it does not have its own init with coder, and the one above it calls init with capacity, it will call the init with capacity of the subclass, not the class that implemented the init with coder. So this is a very unexpected code path that I think most developers would not expect when they're creating a new NS data class or anything like that. So that was quite problematic. So we found a bug that involved this problem. This was in a class called pfarray, and it had init with objects count extended. And this is another very common function. This is typically how you initialize an array. And the problem with it is that it didn't create references to any of the objects in the array. And I'm assuming that this subclass was intended to be used in some very special circumstance where there were already references to everything. But it wasn't. Because of this behavior, basically anyone who deserialized anything could also deserialize this class, which has no references. So this was a use after free for every item in the array. But we moved on, and it got more complicated. Because here's a question. What if an object has cycles in it? What if I say, my NS array is, or my NS URL has the string, but my string has an NS URL, and they just kind of go forever? And this is actually quite interesting. So to start off, how does something get deserialized the very first time you deserialize it? Well, it's called, let's say, NS_SUM class. It gets allocated, and then there's a temporary dictionary, and it gets added to it. Then initwithcoder gets called, and then it will get removed from this temporary dictionary and added to a permanent dictionary. Now, what happens when you deserialize it the second time? Well, if it's in the temporary dictionary, it will copy it and pull it out. If it's in the object dictionary, it will copy it and pull it out. Otherwise, you have actually not deserialized this object, and you have to do that. So that's interesting. There's kind of two problems here. Problem number one is because of that temporary dictionary, you can grab the object before you're done the initwithcoder. And that's like violating all sorts of expectations the programmer has. There's also this problem where initwithcoder is not guaranteed to return the object that is allocated initially. The documents say it can return something different if they want, but meanwhile, this temporary dictionary has no references. So theoretically, you could follow all the documentations and end up with something that has use after free in it. And I actually didn't find any bugs like this, but I found it a little disconcerting that even as documented, you aren't guaranteed to always have references to things where there should be references. So looking at cycles, we found a couple of bugs. There was this one in the NS shared key dictionary. And basically, this is a dictionary where you get optimization in return for declaring all your keys up front. And all these keys are in a singly linked list. And the bug here is that you would go in the initwithcoder, and before your linked list was complete, you could use the object. And the problem with this is that the first time you use the object, it allocates an array that has all the elements in it. And then when you unwind, you'll add more stuff to this linked list. And then when you actually try and access those keys, you'll read out of bounds. And this is a very exploitable bug, basically, because it does calls on this out of bounds reads right away. And I have this picture here. This is just because people are always like, Natalie, do you have special tools that create objects for you? And the answer is no. I hand forge them one by one, and it takes days. So that is how I made this bug work. I'm including this. Stefan Esser put this on Twitter this morning. He made a tool that, at the very least, if you already have the object, it'll display it much more nicely than mine. We can't all be talented. But I thought this was pretty cool and probably a better visualization than this. So there was another bug we found that was similar, and I think this one's a little intuitively easier. This is also in an optimized dictionary class, but this one, it would deserialize an array, it would deserialize the array length, and then it would do stuff, and then it would check that the length was correct. And you had this problem because of cycles. You could cycle back and use this object before it was complete, so there was actually no guarantee that that length was correct. And that ended up being an out-of-bounds write. So those were all the bugs we found. So I'm going to end off by talking about, why were there so many bugs here? And the reality here was that this deserialization presented a huge attack surface, and this subclassing and library behavior made it worse. The problem was every time you included a library, all this deserialization code got included, even if that wasn't intended by the developer that wrote the library. And even if you're using that library for something that is completely different, even if you're never even using that deserialized class in the library. And I'm happy to say that this has been improved in iOS 13. Now deserialization doesn't allow subclassing. Now if you deserialize an array, it will just call the array initwithcoder. I think that's great. I think that would have prevented every bug but one we found in this research. So that's it. In conclusion, fully remote bugs exist. We've reported 10 bugs total in iMessage, and I think I've found about 4 in other messengers at this point. Most remote bugs exist in native code, but every so often there's a great logic bug, so don't ignore that avenue either. I found that design problems with iMessage and serialization made this an especially bug-prone surface. So I think there is a lesson to be learned here as well in how to design a messenger, because definitely there is a big gap, in my opinion, between the ones that are easiest to find bugs in and the ones that are hardest to find bugs in. And finally, we released some tools for this research. This top one is the iOS messaging tool. These are the ones that will send and receive iMessages. And then there's also these video conferencing tools below, which can also be helpful for finding bugs that logic bugs might be able to make remote. So that's it. Thanks a lot. I don't think we have any time for questions, but stay tuned for Samuel's talk about how to exploit these bugs. Thanks a lot.